So before I get started, let me get to know my audience a little bit. How many of you folks heat your homes with oil or natural gas? Like the vast majority of people. How many people have a couple cars at home? Okay, again, the vast majority of people. Okay, and now how many people would like to save $7,000 to $10,000 a year in their energy bills? Okay, that's what we're going to talk about today. Oh, one more question I forgot. How many people have air conditioning at home? All right, again, the vast majority of people. So I think this is highly pertinent. So we will talk about solar and energy storage, both at the town level and at the individual level. So what you're seeing here is this week's the last week's production from the Hartwell Solar Energy System at the Hartwell composting facility. So many of you are very much aware of what the benefits of solar are. That solar is, 10 years ago, if we were talking about this, we couldn't have put this first bullet up, but today solar is the lowest cost source of energy in the world. It lets you have fewer power plants, it improves resilience, it creates local jobs, and of course, there's substantial health and climate benefits. The picture on the right I wanted to show you is something that's published by ISO New England 4 or 5 years ago, when for the first time in New England, the solar power generated enough solar to lower the peak demand for the entire New England to lower than at midnight. And so what they're showing is what is the ISO New England version of our duck curve and giving you an indication of how much power is generated by solar. Again, this is about 5 years ago. If you go underneath, you'll see these are, I don't know if you can see my cursor, you'll see a couple duck curves from this year that I occasionally capture on my phone, and you can see that on March 29th of this year, we were well below the ISO New England power plants needed to generate way less at noon than they did at midnight. And similarly on April 30th.
What is duck curve? What do you mean by duck?
People claim this looks like a duck, so they call it the duck curve.
What have they been drinking?
You have to sort of get really sort of creative with this, but basically that's what people call it, as a duck curve.
I've got a question. That curve showing this solar power, that's not power that's on the grid. That's power that's being generated by individuals, or what?
Yes.
Because the grid power from solar is a few hundred megawatts.
Exactly. So there's plenty of grid power. But what you're looking at here, the big effect when you look at these sort of forecasts versus actuals, they're taking into account what they call behind the meter solar. So when you put solar on your roof, you hook it into your electrical panel, quote unquote, behind the meter, so that you power your own equipment and your own air conditioners or whatever before it goes out onto the grid. What ISO New England reports is front of the meter solar, and what is actually installed, much of that is behind the meter solar, which ISO New England can't see except by the behavior of the peak demand curve you're looking at here. So this graph with the yellow solar power is actually published by ISO New England about 5 years ago. So it comes from ISO New England. It's not made up, it's their numbers. Okay, so what we can talk about is solar. And a lot of people say, well, solar doesn't work at night, so we're concerned about whether we should be adopting solar or not, because it doesn't operate 24/7. But the interesting thing is, yesterday, you're seeing significant heat waves all throughout the country. And what happens during these heat waves is you tend to have not very much wind, and you tend to have a lot of solar radiance right at the time when everybody's turning their air conditioners on and is looking for the absolute peak demands. And so what you can see is that when we're having one of those heat waves, the cost of electricity in these grids goes up substantially, sometimes orders of magnitude. Yesterday in PJM territory, which is from like Ohio out to Virginia, they were paying $2 a kilowatt hour for their electricity, whereas normally they pay about 5 cents a kilowatt hour for their electricity.
Megawatt hour.
They were paying, excuse me, $2,000 a megawatt hour, $2 a kilowatt hour. Sorry, yes. Exactly. So when you look at solar, you have to look at, you know, what if you don't do solar? If you don't do solar, you're going to have more power plants, pipelines, transmission lines. You're going to be using more fracked natural gas, coal, and oil. And the waste thing, not a lot of people, you know, the ones that I just mentioned are obvious to many people, but a lot of people think about the waste. So this comes out of Lawrence Livermore National Laboratories. And what it's showing is Massachusetts' total energy use. And it's a really interesting Sankey diagram that I really like to look at a lot. And the gray area that you're looking at here is, I'm sorry, get the cursor in the right place. The gray area is rejected energy. And what you're going to see if you do the math on the gray area for electricity generation, you'll see that roughly 66% of all of the energy we put into our power plants goes up the cooling stacks or is wasted or is lost during transmission. So only about a third of the energy we put into our power plants actually makes it to our houses or our businesses. The other area of massive waste is in our transportation system. So our cars, when we put a gallon of gasoline in our car, only somewhere on the order of 80% of that heat value of the gasoline we put in our car goes out into the atmosphere, doesn't actually move the wheels forward. So we have massive amounts of gains we can make if we can figure out a way to eliminate this waste that's in our current energy system. So before we start talking about solar, I just wanted to talk a little bit about some of the other major trends, energy trends in the world today. And as you have probably all realized, we're seeing massive increases in fossil fuel costs over the last year and a half. And so what I wanted to do today was sort of to take a look at what our energy budget was 2 years ago and what our energy budget is today, and give you a little context of how we got there. So if you look right here in 2020, and if I could have gotten a graph that goes all the way back to 2016, you'll see that natural gas prices at the Henry Hub, which Henry Hub is in Louisiana. It's sort of the price setting location for natural gas in the United States, was about $1.75 per million BTUs. And now we're at, this graph is about a week old. We're at 8. Since this point in time, it's gone up to $9 per MMBTU at the Henry Hub. I think it was $9. Oh, I have it here. It was $9.28 last week. So it's continuing to go up. And the interesting thing here at the top, you can see it says Algonquin Citygate spot natural gas prices. That's what we pay in New England for our natural gas prices. So we pay a lot more for our natural gas than is paid at the Louisiana Henry Hub here in New England. So we're paying something on the order of $25 to $27 a BTU. And we used to be paying just a year ago, right around $3. So we're seeing massive increases in the cost of natural gas. So now let's take a look at, go back to Lexington. Let's take a look at what we're paying for electricity. And what you're looking at here on the bottom is what Eversource's delivery charges are. And there's a bunch of different components in that. I can walk you through those if you're interested. But as you can see, the cost for delivering, not the cost of the energy, but the cost of actually, the poles and the wires and the maintenance of the poles and the wires has been going up pretty substantially over the last 4 years from an electricity perspective. And the green bars up here is what Lexington's Community Choice has locked in for a number of different periods for our supply price. And the interesting thing is that for the last 18 months, our price is actually lower than it was for the previous 18 months. So what you're seeing here is that natural gas prices, if I go back here, the impact of on our natural gas prices in 2020, in 2021, Lexington natural gas prices during the height of the winter were $1.49 a therm, and at the height of the winter this year, January of 2022 to March of 2022, they were $2.02. So it's a substantial increase, but not yet reflecting this big increase that is actually being paid by the utilities for natural gas. So we can expect to see our natural gas prices rise again because the way the natural gas companies buy natural gas, they buy it in fixed periods of time. So they've got a little bit of sort of leveling out of this sort of massive price spike that you're seeing. The interesting thing is that electricity prices don't tend to go up anywhere near as fast as natural gas prices. And the reason is for exactly this reason, as I pointed out here, we've got half of our cost of delivering electricity. Half of our cost of electricity is delivering the electricity, maybe a little bit more even right now than that. And that has no natural gas prices have no impact on that. The other interesting thing is that natural gas makes up only about 50% of our grid. We make power from solar, wind, nuclear, and other sources. So natural gas is only half of the cost of the energy supply part. And interestingly, in New England, we also pay about half of our energy supply cost as something called capacity. And so when you see natural gas prices go up by a factor of, let's just say natural gas prices went up by a factor of 8, not true, but just to make the math easy. The impact on electricity is for delivery is you divide by 2 for delivery, you divide by 2 for the fact that natural gas is only 50% of our energy used to produce power, and then we have another 50% of supply is based on capacity. So essentially, when you see a massive increase in natural gas coming to your home for your boiler, it's ameliorated in your electric rate by roughly a factor of 8. So if we take a look at solar, this comes from Lazard. It's one of the best industry sources for that's been running this analysis for 10 or 20 years now, every year. And what they're showing is what is the cost per megawatt unsubsidized for various different sources of electricity, whether that's gas peaking power plants, nuclear power plants, coal power plants, or gas combined cycle. And what you're seeing here is that utility scale solar is by far and away the lowest cost for electricity. The interesting thing here, these little sort of gold diamonds, that is the cost for running a nuclear plant, a coal plant, or a combined gas and cycle plant that is fully depreciated. So essentially, assuming we have a plant, we fully depreciate it, and we're only paying fuel costs and maintenance costs. So what you're starting to see now is that solar can provide roughly the same amount of cost as a fully depreciated coal or nuclear plant. And when we see natural gas prices doubling and tripling as they have done over the past year, you'll start to see the gas combined cycle move closer up to the price for nuclear and coal plants. So that's sort of the global view of energy. What does it mean for Lexington's household energy budget? And what I tried to do is take July of 2020 and take a typical home in Lexington, which uses about 750 kilowatt hours of electricity, uses about 930 therms of natural gas, and has 2 cars, and they're driving about 12,000 miles each. And using the similar heat load for oil, and what you'll find out is that in 2020, we were spending about $5,500 for all of our energy needs, for electricity, for heating, and for transportation if we were heating with natural gas. And we were spending about $6,000 a year if we were doing that with oil heat. Now in 2022, we've seen a massive increase in our cost of gasoline. That's this top yellow area. We've gone from essentially $2.20 or something to $5. So somewhere on the order of 2.3x in terms of our cost of gasoline. So that's a massive increase in our energy budget. We've also seen that oil is almost the same. It's gone up about 2.5 times during this period. And as I mentioned before, because we buy our natural gas through utilities who sort of level out, they buy long-term contracts for natural gas, we have yet to see the impact of the natural gas price increase hit us for people who are on natural gas. But the fact is that today, March of 2022 natural gas prices and July of today's gasoline prices, what you're starting to see is that you're about $9,000 to heat your home with natural gas and drive your cars, and almost $12,000 if you're on oil. Now the question is what can you do to lower that cost? If you switch to all heat pumps and all electric cars and power that all with community choice electricity, you can drop that down to about $5,000. So lower than the cost you were doing this for in 2020. And if we go solar, if we put enough solar on our roof in order to provide our electricity, that solar electricity is going to cost about 1/3 of the amount of our community choice electricity. So that's how you get to a savings of somewhere between $7,000 to $10,000. 7 if you're on natural gas, and $10,000 if you're on oil, by doing 3 things: by switching to heat pumps, switching to electric vehicles, and putting solar on your roof. Now, of course, that has a significant difference in terms of emissions. Even if you are powering this off of the ISO New England grid, we have one of the cleanest grids in the country. ISO New England does. So when we switch our gas, because there's so much waste in our fuel, sort of 4 to 1, 5 to 1, depending on how you look at it, you'll see that our emissions are actually lower because the heat pumps are so efficient and because electric cars are so efficient. They're essentially eliminating massive amounts of energy that doesn't need to be burned because you're electric. And then again, if you are now supplying your electricity with your own solar on your own roof, you'll still have some emissions, but it's orders of magnitude lower. So can you actually do that in Lexington? So many of you may have been familiar with LexHab, the Affordable Housing Authority, and that builds affordable houses in Lexington. This is something called Farmview. They call this 3-family location, Farmview. It's essentially a net zero home. They have a small minor, maybe 1% of the energy that's needed comes from the grid versus 0, which would be a true net zero home. So this place got close to net zero. And this is Farmview, which is down near Lex Farm. They built 2 units that look like this. with solar on the roof, and solar can provide all of the, and these are, by the way, Farmview and Fairview are all electric homes. So they do all their heating, cooling, cooking, everything with electricity. So the solar on the roof is providing all that power. So what does that cost? What would it cost if I wanted to do a heat pump and power it with solar? So these are today's numbers. If I needed to generate 17,000 kilowatt hours of electricity a year to power my heat pump and my home, I would probably need about a 13.6 kW solar energy system on my roof. That probably cost about $44,000. And in the first year, after tax credits from the federal and from the state and savings from your electricity and smart incentives, you would generate about $18,000 off of that 44. You'd essentially, at the end of the first year, that solar energy system would have cost you $25,000. And you can see that the smart incentives are worth about $10,000 or $11,000 over 10 years, and then they end after 10 years. And what this will show you is that essentially you have a 5-year payback. So you put your $44,000 worth of solar on your roof, and at the end of 5 years, you're getting free electricity. There's another reason you might want to consider moving to heat pumps soon, because if we're starting to see that it's possible to save, you know, $3,000, $4,000, $5,000 a year by switching to heat pumps, more and more people are going to do that. And remember when I talked to you before about the fact that the distribution system for electricity, about half of our costs is in distribution delivery costs, and about half of our costs are supply. In natural gas, it's a very similar situation where the natural gas company bills you for the pipes in the street and the cost to maintain the pipes in the street. And that's essentially a fixed cost for them to maintain that network. Excuse me. But if you could imagine a situation where more and more people are saying, hey, I really don't want to spend $5,000 or $6,000 or $7,000 on heating my house a year. I'm going to switch to a heat pump in order to save some money. You might see, and this is a fairly a conservative look at this, you might see people move from about 10% heating with electricity today to say maybe 20% heating with electricity in 10 years. That doesn't move the needle very much in terms of the fixed costs that are now being borne by, instead of 100% of the customers, now by 90% of the customers. But you can see that this rapidly changes on an exponential level. The next 10 years, you start to see that just the delivery costs, not the energy supply costs, but the delivery costs potentially can go up 8 or 9 times. So instead of paying $1 a therm for delivery of your natural gas, you could easily be spending $9 a therm 20 years from now as people abandon the natural gas network for various reasons. So one of the things that we need to be thinking about is, how do we accelerate the amount of solar power that people are putting on their roofs? Right now, there's a 10 kW AC limit. It works out to about a 15 kW DC limit, given inverter ratios. Senator Barrett has a Senate bill that's in conference committee right now. Section 44 of the Senate bill raises the residential net metering capacity limit from 10 kW to 25 kW. So if you care about being able to power all of your house, your home, and whatever, ask your rep, Michelle Shikola. The House has to go along with this, or your senator, whether that's Senator Friedman or Senator Barrett. Let them know Section 44 of Senate Bill 2842 is important to you. Another thing that we want to be able to do in order to move into this world where we're all electric is we want to start integrating energy storage systems into the grid. And one of the key things we need to enable in legislation, right now not allowed in legislation, is for energy storage systems to net meter, essentially to buy electricity at low prices and sell it at high prices. Right now, that's not allowed. So now let me talk a little bit about Lexington. So in Lexington in 2018, now 4 years ago, we set a 25-year goal to reduce greenhouse gas emissions from all of Lexington's residential, commercial, and municipal buildings by achieving a transition to 100% renewable energy sources. So we have until 2043, according to that time frame, in order to make that transition. And why did we say we wanted to focus on our buildings? It's because if you sort of look at this map, this pie chart of all of Lexington's emissions, you'll see that 6% of our emissions, this was our baseline we did in 2012, were coming from electricity, and about 30% from heating our buildings. So you got about 66% of all of Lexington's emissions were from our buildings. And so that's the plan. So let me show you a little bit about what we did. Harrington School, we put solar panels on 5 schools and the Cary Memorial Library in 2014. We put 2.2 megawatts of solar out on the Hartwell Avenue composting site. That went live in 2017, just about 5 years ago today. And you can see this is the way the Hartwell Avenue composting site looked before we put the solar on it. If you look in really carefully, you can see that it's hazardous waste recycling day when Google was flying over, as you can see everybody in the line waiting to drop off their hazardous waste at the hazardous waste temp there. And this is what it looks like today. We took the hazardous waste site and we put a solar canopy over the hazardous waste site. We put a solar canopy nearby where you drop off your brush or your leaves. And the rest, we put about 1.4 megawatt solar array here on 4 acres of land. And this is another sort of aerial view that's a little easier to see than just straight down, that gives you an idea of where we are. The interesting thing about this, if you look back at this picture here, the town of Lexington is making money from doing composting on the composting facility. Essentially, residents drop off their leaves and their brush, and it gets put into what these lines are called as windrows. And essentially, we charge a tipping fee for people to drop this off if contractors are dropping it off or other towns are dropping off their composting here. We turn it into valuable compost material and then sell it. At the time we started this project in 2014, we were doing something on the order of $100,000 in revenue from composting. And there was a big concern that if we put solar on the facility, we would lose revenue as a town. So what we suggested at the time was that at the time these windrows were being made with front loaders. And we suggested that it might make sense to buy something called a windrow turner that would double or triple the yield of our composting facility. And just yesterday, I received an email from Robert Bowden of the town's DPW department that says that when we put the solar in, we bought a windrow turner at the same time. It's a $500,000 piece of equipment. And it has done exactly what we thought it would do. We are now generating $1 million a year from the composting facility, from the smaller area of composting that we have here, because we're doing it much more efficiently than we previously did. And on top of that, this solar is generating revenue for the town. Let me just show you this here. In 2021, the rooftops, those 1.1 megawatts of rooftops, are generating about $173,000, and our Hartwell Avenue site was about $370,000. So we're about $533,000. Now, the interesting thing, the magic thing about solar revenue is that when Eversource raises their rates, which they have just done substantially in July of 2022, it raises our solar revenue because we negotiated fixed costs that we pay for the solar revenue that comes out of the schools and the Hartwell Avenue. And what we're going to be seeing is our revenue from solar in the town of Lexington will go from $533,000 in 2021 to $807,000 in 2022. That's a massive increase in revenue. So we essentially have a hedge against energy prices. When we're starting to see energy prices go up, our solar revenue, our solar energy systems are acting as a hedge on the town's budget. So now let's talk a little bit about what we did at Hastings School. Hastings School is a net zero school. And at the initial phase of the school, when we started designing this in 2013 or 2014, something on that lines, at the time, the conventional wisdom was it's impossible to have a 3-story building that's a net zero school. And we said, well, what's the problem? What's the issue with that? And they said, well, the issue is that we're going to have air conditioning systems all over the roof, and there's not going to be any space on the roof to put solar, so it's impossible. We said, well, what if we put ground source heat pumps in to the school and thereby lowered the amount of ventilation systems that need to be on the roof and also lower the amount of electricity that we need at the school? And they said that would be great. We can cover the whole roof with solar energy panels, but we're still only going to be able to generate 1/3 of the power the school needs. And so then we said, well, what about out in the parking lots? What if we put solar canopies out in the parking lots? I don't know if anybody's driven by Hastings School yet, but the solar panels are now up in the parking lots, and they're generating 2/3 of all the energy that the school needs. So what we've seen is that the school needs about 975,000 kilowatt hours of electricity a year, and the solar energy systems on site are going to generate 1.1 million kilowatt hours of electricity a year, so slightly more. We did the same thing at the Lexington Children's Place, which is near the community center. It's a much smaller building. It's about 30,000 square feet. We put solar canopies out in the parking lot that are capable of generating twice the electricity that the school needs. But the interesting thing, back to energy storage, I said I was going to talk about energy storage at the beginning of the day. So if you generate all of your electricity from solar panels and just all of your electricity from solar panels, you find out that it doesn't drive your electricity bill down to zero. And the reason for that is we pay commercial rates for our schools, and commercial rates come with peak demand charges. And it turns out about 45% of our electricity bills are paying for these peak demand charges. Essentially, we're paying for, if you want to think about it in terms of sort of a pipeline kind of perspective, we're paying essentially for the size of the pipe that's connecting to the school. So solar doesn't really do much to reduce demand charges because solar production doesn't correlate necessarily with when you're using the building. People are in the building when it's cloudy outside. And so the way peak demand charges are calculated is not sort of on an annual basis, but they're calculated on a monthly billing period of 15 minutes. So what essentially Eversource does is look over your entire 30-day period for the highest peak demand period of highest 15-minute peak demand period. So if you have one cloud come over for 15 minutes, essentially you get no value for your solar for that entire month. And then of course, you can see that as Eversource changes their rates, it's very possible that they could increase demand charges and lower per kilowatt charges and change this 45% to 50% or something along that lines. And energy storage can help you in all three of these areas. So let's take a look at some graphs from Lexington High School. So what you're seeing here in blue is the building's energy demand, and what you're seeing here in yellow is the solar power that's produced from the roof on the top of the high school that we installed in 2014. And so you can see that it's quite normal for the building to turn on before the solar starts generating substantial amounts of power. So
What is that going to
essentially-
look like? What is that going to look like in January? I mean, here you are in July.
Exactly. You're 100% right. I got what I'm showing here is sort of the optimal best case for when solar could impact demand charges is during, summer months. It has even less capability to impact demand charges during the winter months. It turns out, interesting enough, solar does its best in the shoulder seasons, in the April timeframes, in terms of offsetting demand. So this is but anyway, so we modeled the same idea with Hastings and said, if we're able to generate all of the solar all the energy needed for the entire building with solar, how do we also manage this from a peak demand perspective? And we modeled what you're seeing here now is the solar production. This is now in a shoulder season, and this net demand is what Eversource sees at their meter. And so the idea is, in green, you're seeing a battery that would charge when solar is generating, and essentially, excuse me, would during peak demand times, which change throughout the year. So you have to program this in some software, but you would turn the battery on to lower your peak demand during peak demand times. And then during off-peak demand times, you recharge the battery during off-peak time, so it's ready to go to offset the load during the next day. So what you're seeing here is that you can, whatever source sees is a substantial reduction in peak demand. So here you're seeing that we're doing 300 kW as a peak demand for this particular week, but the battery is shaving that down to less than, where is it here? So here during a peak demand time, it's under 200K. This is during an off-peak time, so that's not what Eversource bills you for, not that right there. I don't know if that's helpful or not, but the interesting thing, so let's turn this into dollars and cents. So here's your 900, so if we didn't have solar on Hastings School, our electricity bill, this is an old slide, I should tell you. I did this slide 4 years ago. So the electricity bill would be substantially higher today, but $975,000 a kilowatt hour usage at that time would have been about $135,000 in per kilowatt hour charges, usage charges, and about $115,000 in peak demand charges. But when we put solar with a battery and we get 150 kW demand reduction throughout the year, you'll see that we save $23,000 in energy costs on our solar, but turns out way more from the value of having the battery on site by reducing our peak demand charges. The other interesting thing is that the state gives ground source heat pump incentives that double or triple if you are generating the power on site from solar. So this is a substantial increase that comes as a result of having solar on site. The net is that by designing a net zero school, we lowered our total cost of operation and have a net zero school. And here's the
Mark,
yes.
how you're talking about the like the annual savings or something of that sort.
Yes.
What were the costs in building that system How long did it take to recover those?
This is the next slide, exactly. So the answer is it took the very first day of operation were net positive. So the way we look at this as a town is, and you probably look at this the same way as a house, we don't pay cash for Hastings School, we bond it. And so the cost of putting solar and batteries at Hastings School was zero because we had a third party come in and provide us the solar and batteries on a power purchase agreement. So we pay for the solar energy we purchase from the solar on site, but there was zero capital cost outlays. The capital cost outlay that we had was in the heat pumps, in the ground source heat pumps. And so what we did was we modeled a scenario and said, how much more are we going to have to pay for the heat pumps on our debt service? And how does that impact us in terms of our total cash flow? And so we modeled this, I'm sorry, going backwards. We modeled this in 3 different scenarios. We said there's going to be a scenario where we have low interest rates. There's going to be a scenario where we have middle interest rates. There's going to be a scenario where we have high interest rates. There's going to be a scenario where we have low electricity prices, moderate electricity prices, and high electricity prices and peak demand charges. And so what we modeled out here is we said that in the case where we have the worst possible outcome in terms of the cost of our ground source heat pumps, our ground source heat pumps costs were high, and our interest rates for those ground source heat pumps were high. And we said that's the worst case here, is that we'd have something on the order of $120,000 incremental debt service on our cash flow. And then we went over here and said, let's take the worst case in terms of savings. And we came out and we figured out that it would be $155,000 in savings, worst case. So we said, if the absolute worst thing happened in terms of ground source heat pump cost and interest rates, and the absolute worst thing happened in terms of energy costs, would we be okay? And the answer was yes, we would be spending $120,000 on debt service and making $155,000 in energy savings and peak demand savings. What has actually happened is that our ground source heat pumps came in lower than we expected in terms of principal costs, and we bonded at an exceptionally amazing time. We bonded at less than 1% interest for the Hastings School, which was well below even our lowest estimate. Our lowest estimate was 2%, I think. So we bonded about half of the rate, and the energy costs, as we've seen, are now substantially higher. So we are making a ton of money on Hastings School because we did a combination of solar, storage, heat pumps all together and looked at it from a cash flow perspective as opposed to a initial cost and return on investment perspective. This is at the same time we're doing Hastings School, we're doing 7 other schools putting canopies in the parking lot. You may have seen this. This is Harrington School conceptual, but if you go to Harrington School right now, or Diamond or Clark, you can see that there are canopies up in the parking lots there. So now let's go back to residential energy storage. So a Tesla Powerwall, Tesla Powerwalls come in 14 kW increments. So you'd need 7 Tesla Powerwalls to have 98 kW worth of power and provide about 4 days of power back up to your home. If you're just using electricity, you're still using fossil fuel, natural gas or oil to heat your house, and you're still using gas to drive your cars. But this 98 kilowatt hour backup would give you 1.5 days of power backup if you have transitioned your house and your heating system and both of your cars all to electricity. So right now, a typical Lexington house is using about 25 kilowatt hours a day. And a typical Lexington house, if it was 100% electric, would be using about 63 kilowatt hours a day. So here's the fun part. A Ford 150 Lightning comes in the base configuration with 98 kilowatt hours of power in it, and it is set up in a way that comes with a charger, a two-way charger that will allow you to back up your home with the truck. And it will give you this same 1.5 day power backup for your home, your heat pumps, and your electric vehicles. So let's look at Ford versus Tesla. The base price of a Ford 150 Lightning is $40,000. It comes with this 98 kilowatt hour battery that works out to a little over $400 a kilowatt hour. If you want the extended range Ford 150, they make you go up a couple models on the Ford 150 and buy all kinds of other premium stuff to go along with it. And the base, the lowest price you can pay for a Ford 150 with 131 kilowatt hour battery works out to about $550 a kilowatt hour. The interesting thing is Tesla Powerwalls installed are about $12,500 for that 14 kilowatt hour battery, or close to $900 a kilowatt hour. You'd have to spend $87,500 to get that same 98 kilowatt hour battery that is in your Ford 150. So I don't know how you want to think about this, whether you want to think about this as I bought power backup for my house and I got a truck for free, or I bought a truck and I got power backup for free. And this $40,000 doesn't count the incentives that come from Massachusetts for buying an electric vehicle. So that's really what I had to say about this. This just gives you sort of an idea of the magnitude of solar that's possible to be generated versus the total reserves we have for fossil fuels. And so the interesting thing is if you take a look down here in the lower right, it says we have 900 terawatt years of coal reserves left, but we have 23,000 terawatt years of solar potential per year. So it sort of gives you an idea of the scale that of solar potential. So anyway, there we are. Now happy to take any questions.
So what do you do about snow in the winter and all those nice?
You don't do anything about snow in the winter.
What happens to your solar radiation when those
Okay. Well,
panels are all
I'll show
covered
you.
with 6 inches of snow?
They don't generate any power. I'll show you what, let me see if I can find it here. Do I have it somewhere in here? Okay. If you go back, yeah, here. This is Hartwell Avenue solar production for the year on the bottom. And so what you'll see is this is last year. This is July of 2021 until yesterday. And you'll see in February, when we have a good snowstorm, you get very little snow, very little power. But overall, it's not material in the course of a year. So yes, you will need to be backed up to the grid. You need to be getting power from the grid. We're not advocating here for an off-grid solution, because you're right, you're not going to have enough power to make it through the day in an off-grid situation in February when it snows.
I have a question about this whole idea of looking at these things both from the energy perspective and the financial perspective. The financial perspective we know is a giant multi-dimensional Ponzi scheme. We don't really know what the cost of any of those kind of things are in the ultimate sense, other than what we can measure directly, which is the cost of generation and transmission distribution for the electric grid. We have experience that goes back decades on that. These other things, we have no life cycle experience on them. We have no way of knowing what the cost of disposal is, for instance, on these things. So there's no way to really measure the cost factors, but what you can look at is the energy factor side. And on the energy factor side, you have a real problem. And that real problem is that, yes, on a aggregate kind of a basis, you can find there's plenty of solar energy. And there's also plenty of wind energy and plenty of wave action energy and all that. But when reality comes to hit the fan, to try to build an electric grid around these things, it doesn't work. It doesn't work because you need power that you can call upon when you need it, as you need it. And none of those things are capable of delivering under that condition. Even the battery storage combined with the thing, okay, fine, I've got 96 hours of energy storage, and then my problem is now I have a week with essentially no sun and minimal wind, which we can get, in a occasional situation in a winter time. Once you've reached 96 hours, what happens on your 97th hour? You go to the highest bidder for whatever's available on the spot market. And this is a problem. And the countries that have embedded themselves with this idea that you have all this free energy available, you just pay the capital cost, and that was fake because we had fake money for the cost of interest. That's all coming to an end. Germany and all these people are looking at it and saying, wait a minute, maybe we went over the line on this side. Whereas a reliable system that based on nuclear, available hydro, and combined cycle natural gas, we can build a system that gives us reliable electricity on demand whenever we need it, and supplement it, sure, of course, whenever you have a chance, but you can't possibly depend on solar and wind as a base source. It just isn't going to work.
Bill, what's your expertise in utility planning? Or is this just something you read on the internet, or is or do you
No,
actually have
I
some
was on the City of
expertise?
Austin Electric Utility Commission for 3 years, and we were at that time experiencing very rapid growth in demand, as it is happening again now, but this was a number of years ago. And we looked at every possible reasonable source. Now, solar was much less developed, of course, it was back in 1980 time frame.
Yeah, say the least.
But the Charles T. Main Company was hired by the city to do the legwork for the commission, because just lay people.
Okay, in 1980, you could not have built a wind, solar, storage, hydrogen system, but it's not 1980.
No, of course, but the problems are still there. They haven't changed.
No.
You cannot tell me if I say I want a megawatt
Ted,
from your solar array, and you
Ted,
say, I'm
please
sorry,
let
a
Paul
cloud
finish.
just came overhead.
Ted, please let Paul finish.
Yeah.
Paul,
Okay,
go ahead, please.
So in your system that you would prefer, first of all, you would have to pay the enormous cost of building nuclear power plants. But if you somehow magically managed to build nuclear power plants that weren't, 4, 5, 6 times as expensive as wind or solar, then you would still have the problem that they don't follow load, and you would need something that would. So you'd need your combined cycle plants. Where do you get the fuel for those? You can get the fuel for those from hydrogen produced by wind and solar in off-peak times when they're overproducing. So you can do all this, and your speculation that it can't be done does not seem at all plausible. And Germany is not pulling back on renewables. They're stepping up on renewables to get rid of Russian gas. They screwed up in shutting down. They screwed up in shutting down so many nuclear plants so fast and putting themselves at Russia's mercy on the gas. But it'll be, another decade before they could get a new nuclear plant built. And in that time, they can get a lot of wind and solar and storage built. So don't be so pessimistic. That's all.
No, I'm not pessimistic, and I'm not saying that you can't look at these things on a long, very long-term schedule. You know, because I think then you have fusion plants, for instance, that you can put in place of where your existing plants are inside the metropolitan areas and things like that. But in the short term, in the time frame between now and say 2040, the only viable system, and there's no argument, I think, if you look at it on a realistic basis, as opposed to, you know, some sort of a dream world, the only realistic basis is combined cycle natural gas plant as a peaking unit whenever you need it, base load power coming from whatever you can get the base load power from. If wind and solar can contribute, fine, no problem. But the point is, you cannot on a scheduling basis, because the way we do our energy in the ISO is we make long-term contracts, and then there's spot market coverage whenever there's a gap. And
Ted, please, there's a bunch of people that want to ask questions on the list. Paul,
I left the web address for the ISO New England thing, so you can see what's actually happening as we speak right now.
Thank you.
Yeah.
Paul, before we go to the questions on the chat and the people raise their hand, just a quick background. In fairness, your background for utility stuff?
Yeah, I started working for the Massachusetts Attorney General in utility regulation in 1977, and I have been consulting on utility planning and regulation issues since about 1980. So, you know, I not only know how the system works now, I know how it worked previously, and TED is not really reflecting the rate of change since 1980.
Fair enough. I just only wanted to, you asked Ted for his experience, and in fairness, I wanted to get yours as well. So
absolutely fair. I just didn't want to brag.
No problem. Carl, you had your hand up first, then we're going to go down to Ken and Harry, and we have a bunch of things on the list.
Yes, thanks, Peter. So there's both some comments and a question. So actually last month, we converted our central air conditioning system to use a heat pump. Of course, we haven't needed any heat this time, although the new heat pump system is actually more efficient at air conditioning than our old system was. So we expect to get some benefits even now in the cooling months. But anyway, we did get its air source heat pump, and at least my limited understanding has been that it's not that practical currently to get ground source for residential, that it's it's just too expensive, and there's hardly anyone around who's actually experienced at installing that. But anyway, so we have kept our gas heating system for two reasons. We don't have other gas appliances in the house. We have electric dryer, we have electric stove, but number one is hot water. That my heat pumps, I believe, are not capable of producing high enough heat to give you useful hot water, and that people who do use systems, heat pump based systems for that, really actually use electric resistive heating, which is fairly inefficient, although certainly is something you can do if you want to get completely off of gas. The other thing is the question of what happens in the coldest days and nights of the winter. And I have to say, I've gotten very mixed information on that. Although our Bosch heat pump is, I think, rated that it will run down to about 0 degrees. We were advised by the installers that, it gets pretty inefficient, say down to at 20 degrees and below. And so you should run your gas furnace at that point. So I do want to hear if anyone has any better information about that. But sort of lacking that, it seems that I can't get completely off of gas.
So thank you for bringing up air conditioners. I actually meant to include this in the talk. So many of the people on the call probably raised their hands, said they had air conditioners, and many of those people probably have air conditioners that are old enough to vote. And that means that they're probably using R22 Freon as the refrigerant. And so what you're starting to see is that R22 equipment was not allowed to be manufactured from 2010 forward, and R22 Freon was not allowed to be produced after 2020. So people like me who have older air conditioner systems, I have central air conditioning at the house. It was put in, if you can believe it, in 1986. And so I am in a month, July 11th, getting the whole air conditioning system replaced with heat pumps. And so the incremental cost for a heat pump versus replacing with an air conditioner is minimal. And I would have had to replace it in any case because it's well past its expected lifetime and you can't replace anymore with existing refrigerant. So from a cost perspective, it makes a lot of sense to put a heat pump in instead of an air conditioner because the incremental cost is low and you get easily heating in the shoulder seasons as well as more efficient air conditioning. So if you have, like I do, a 1986 or even a 2000 air conditioner that's a SEER of 10 or 8 or 6, the current heat pumps are coming out with SEERs of 19, so they're about double the efficiency of your current air conditioning system. Now, a very fascinating question that you raise about what happens when the temperature goes below zero. So what do you think is the amount of hours on a percentage basis in Lexington where the temperature goes below 0 Fahrenheit on an annual basis? Anybody have a guess?
Less
Well,
than 10.
I looked at it for Newton and it was incredibly small.
Yes, it's so the design temperature, the 99% design temperature for Lexington is 2 degrees Fahrenheit. That means that 99% of all the hours of the year are above 2 degrees Fahrenheit. So if you do it, I don't remember, I don't have that spreadsheet open in front of me right now, but I do remember that about 50% of all the heating hours, all the heating degree days are above 32 degrees Fahrenheit. So when you look at these new heat pumps, these cold climate heat pumps, you're right, they do tend to decline as you get below 0 degrees Fahrenheit, but they do rate themselves all the way down to say -14. And I'll give you another trick question. How many hours do you think Lexington has had in the last 10 years at -14 degrees Fahrenheit?
0.
The answer is 0. 0, none. The trick question is we had 4 hours at -13 out of 87,600 hours in the last 10 years. 4 hours. It happened 2 hours in one year and 2 hours in another year at 2 in the morning. What do you think is the average temperature for the day on those coldest days of the last 10 years? It turns out it was 1 degree Fahrenheit. So it turns out that on those super cold nights when it's -13 degrees, guess why it's -13 degrees? We have no clouds. So we're radiating heat up into the atmosphere. The next morning, the sun comes out and drives the temperature up to about 12 or 13 degrees as a high. The average temperature for the day is 1 degree Fahrenheit on the coldest days of the year. So what I'm hoping, and I haven't got mine in yet, it's going in a month. I'm hoping that I'm going to be able to carry 80–90% of my heat load for the year with the air conditioner replacement.
Thanks. Ken?
Yeah, thank you, Mark, for your presentation. I don't dispute anything in particular. However, I'd like to bring in the big picture. Now, nationally, according to the DOE, solar has provided only 3% of what we need annually. And it's not projected to, in our lifetimes, ever provide the bulk of our energy. So we have a real problem in this country and worldwide to provide the bulk of our energy, especially in a carbon-free way.
So yes, Paul mentioned this before. We certainly wouldn't be advocating that provide the majority of the power on a national basis, on a Massachusetts basis, or even on a Lexington basis. What we do suggest is that solar and wind are highly complementary. If you look at the math for Massachusetts and offshore wind, it turns out that we can produce 18 times more electricity than we need for the entire Massachusetts from wind turbines offshore and in Massachusetts. We're essentially the Saudi Arabia of wind. We can export renewable energy from Massachusetts if we build enough. And the interesting thing, you start to see this, they're just showing signs from Texas in the last week or so, but it happens in New England as well. There have been studies showing about how it turns out that the wind power generates most of its power in the evenings, and seasonally generates most of its wind power during the winter season. So if you do a sort of complementary matching of solar and wind together, you reduce the amount of stuff you need to make up the difference, whether that's hydro or battery storage or peaking power plants.
Oh, okay, but that optimism is not really in line with DOE projections, which say by 2050, we'll only get about 20% from solar.
I can show you DOE's projections for the last 20 years, and it's kind of laughable. What you'll see is that for whatever reason, the way these projections are made, they don't tend to be accurate. Let me see if I can find a link. I'll send you a link to I'll see if I can find a link in real time here and put it in the chat that shows there's a problematic sort of thing where people sort of assume that the future is going to be like the past, and that doesn't really work out when you're seeing exponential changes in the price of solar.
Mark, that's also, I think, required by law that at least some of the EIA forecasts have to be based on existing policy, and therefore no improvements in policy can be reflected in the forecasts. So you may be looking at DOE saying, well, this is sort of what we have to say on a sort of business as usual. Doesn't mean we couldn't do a lot more.
I just put up on the screen it's not the national thing, but it's ISO New England's projections for how much solar they expect to be produced in the future. And you can take a look at over time, 2015, 2016. I haven't updated this since 2018. I just found it on my hard drive. But what it shows is that the actual increase in solar production is substantially higher than what was projected by ISO New England. And Paul is correct. For very many reasons, they have constraints on the way they are required to make these projections, but they tend to undercount. You can look at it, whether it's ISO New England, you can look at it, whether it's EIA, whether it's WEA, they all tend to undercount the amount of solar that is going to be produced.
Mark, just to clarify, as much as the projections and going forward. If you have to rely on no changes going forward, I don't know how you measure the difference between the inaccuracies of that versus the prospective analyses that you can say, here's the improvements we think we plan to see, and here's how things are going to get better in the future. We have zero knowledge in both cases. You know, we can't say the past is the same as the future, and we don't know what the future is going to be necessarily.
But what
So
we
I'm
do
not
know-
arguing. I'm just saying that there's fluctuation on both
Yeah,
sides.
I agree with you. Yogi Berra would say, you know, it's hard to predict, especially about
the future.
right.
Yeah, yeah.
So he's absolutely right. You're absolutely right. One of the things that I like to do is I like to look at the trends. And what you'll see is that the trends are not linear when it comes to this. They're exponential. And so you may
Fair
want to
enough.
look at the second derivative or not just the first derivative.
Harry?
Sure. Mark, I thanks a lot for putting a lot of stuff in front of us. Very interesting. I'm sort of interested in understanding how someone who is not steeped, or actually is probably not going to get steeped in all of this stuff, should act at this point. In other words, Carl is a adventurous person and goes out and investigates it himself and buys it. I'm not particularly interested in doing that. I'd like to have help like I do with my medical expertise, which is zero, and my financial expertise, which is next to zero. And so are there organizations or advisors who could sit down with you, who actually are trying to sell you something other than their hours of time? Who you could get an answer from on, should I live in in the estate, what's it called? Whatever. A part of Lexington that is covered with trees.
Yes.
And my house is not southern facing, and all these various things. Get lousy TV reception, but I recognize that that's not part of. So, are there people who could give you some advice on what you could do reasonably and what both the capital expenses are pushed against the savings in energy? How does that work?
Before I went forward with my heat pump, because it's a fairly expensive thing, I hired an outfit called Abode, and they do not sell heat pumps. They're the organization that actually watches over the mass save installers and sort of audits them and makes sure that they're actually delivering. And they had a couple people on staff. This one particular guy, Mike Simons, I can't speak highly enough about. He never actually came to my house. I walked him around on a Zoom call, showing him everything around the house. And they basically said, oh, in your situation, you need to be thinking about this. And these are the kind of heat pump installers you should be talking to. And there's these other kinds of heat pump installers that probably wouldn't be a good fit for you. And so they sort of helped me sort of think through the thing, because, you know, to the initial point, I wasn't sure at all that a heat pump would be a reasonable replacement for an air conditioner. You know, is it actually going to do any good for me at all if the air is coming out of my ceiling, you know, because heat rises? And they answered those questions for me. So I had, at $150 an hour or whatever it was, I had some really good confidence that I had somebody that had assessed my house, wasn't doing it in order to make money off of selling me heat pumps.
Right. Okay, thanks.
Mark, are there other people that are in the same business, so that, you know, to Harry's point, that, you know, if somebody's interested in this, they can talk to a few people?
Abode is the only one I know that is in this sort of assessment without selling heat pumps business. That's the only one I know about anyway right now.
Fair enough.
But
Actually, a follow-up on that is Lexington has been very bullish on all this stuff at the municipal level. And at the residential level, they've gotten us onto this sort of community-based rate with electricity. Do you think there's any possibility that Lexington's going to get more proactive in helping people who own houses that are 50 years, 60 years old to make these kind of conversions? Or not to make them so much, but advise them and encourage them.
So the way I became aware of Abode was because Cambridge did that for their residents. So they were subsidizing this sort of analysis. And I have a friend in Cambridge who told me this is the best thing since sliced bread. So I talked my way into the Cambridge program. The previous sustainability director, and I'm guessing the new sustainability resilience officer was looking at trying to find a way to make a program for Lexington residents using this same model. I'm not sure where we are on that, but it's a really good idea, and I hope we're able to pull it off.
Good.
Thanks.
Dick?
Mark, when I try to understand what's going on in energy production, storage, and so forth, I try to look at it from a chemistry, physics point of view. And I'm wondering what you know about, or anybody in the group knows about, the changes in efficiency for solar panels, for heat pumps and so forth. What's happened in the past, but really what's going on in the future, because my understanding is that in solar panel, I mean, the big thing you're trying to do is to make things as efficient or more efficient as you can as time goes on. So I'm trying to see if we're going to really increase our efficiency as time transpires. And my understanding is that in the solar panel area, we've been at an impasse, so we haven't really increased the efficiency of them very much in the last 10 or 15 years. But there's a lot of people who think that they're coming up with processes and materials that will make them more efficient. Do you have any comments on that, or you have any knowledge of what's happening?
Yeah. So solar panels have gotten more efficient over the last 10 years, but it's not like a 10% a year kind of thing. It's more like a 0.5% a year kind of, but again, it's an exponential sort of function. So what you'll see is that panels that were around in 2008 kind of time frame, the evergreen solar panels that were manufactured here in Massachusetts were something along the lines of 185 watts per panel. And now you're starting to see panels now 15 years later that are about 330 watts per panel. Now the sizes have changed slightly, but overall it's somewhere between 0.5% to 1% a year in terms of efficiencies that we've been seeing improving in solar. The heat pumps have also gotten better, but again, it's sort of, there's a big sort of massive change in heat pumps in about, I don't know, 10 or 15 years ago. There was sort of a phase change where people were just, heat pumps were primarily sold in warm climates, and there wasn't a lot of innovation being focused on how to make a heat pump work in a cold climate. They just said that's not our market, and they didn't spend much time on that. But probably about 2008, 2010, Mitsubishi and Fujitsu started investing heavily into heat pumps and making them efficient in a cold climate. And they started putting in two-stage inverters, and now we have variable stage inverters. And so they're much more efficient, but I don't think you're seeing right now. We had this big sort of step change about 5 or 6 years ago. I don't see you're sort of moving dramatically in the future from where we are now.
Hey, Mark, just a quick question on solar panels, if you don't mind. Tesla has a solar roof versus the solar panel. Do you know any differences in terms of efficiency between the two?
Much less efficient.
Tesla is much less efficient?
Tesla sells both. Tesla sells both these sort of standard solar panels and building integrated. So the building integrated systems are much less efficient and they're much more expensive. But the argument is for people who want the roof to look like a roof and they're replacing the roof, if you're sort of combining the two together, the cost of replacing a roof and putting solar panels up, then it starts to make economic sense. We have one in Lexington on Concord Ave.
Yep, I've seen it go up. That's what I was aware of.
Yeah.
Yep. Tony? Thank you.
Mark, thank you very much for the presentation. Every time I listen to one of your presentations, I learn something new. And thanks for your perseverance in moving our town in the right direction, because no matter what the little pieces of information that are missing here and there, this is the direction we should be moving for the future. So again, thank you very much. My question is related to the slide that you presented, which showed that in about 5 years, the cost can be recovered. And essentially, as one of the things that I did this year was have one of these energy audits. Actually, it was done last year. And when they called me, they painted one picture for me. When they came, they painted another picture for me. And when I got figures that would, I'm sure, would not be the realistic ones yet, it was yet another picture. And slowly, I went totally away from them. Just to give you one example, when I talked about solar panels and eventually I got the estimate and so on, I said, well, I need to cut that big oak tree over there in order to do this. Oh yeah, that's shading your roof. Does this estimate include the cutting down of the oak tree? Oh, no, this is. So my basic question is this. Massachusetts right now, or the federal government, is giving tax credits for putting certain systems in your house. Is there any thinking, instead of giving these credits, to undertake a project where they will accumulate all of these estimated credits per year and say these are enough to install solar panels on, let's say, 10,000 homes in the state or 1,000 homes in the state. So we, the state, are going through a lottery system, allow 1,000 people to volunteer to have their house installed with this so that they won't have any hidden costs, any questions. They won't fall into the hands of any charlatans. Does that make sense to try to promote for the future? Thanks.
It's an interesting idea. I hadn't heard of it before, and I think I've heard of many ideas. But so it's rare that I get a new idea. But that's a really interesting thought. So you're suggesting, should the government put solar on people's houses for free and maybe do less of it than they would get with the subsidies, but just completely cover the cost?
Yes, so that they can protect the consumer basically from all of these different consultants that you eventually have to get involved with, each one of them working their register, but each one of them saying, oh yeah, that's somebody else's job eventually.
Well, one of the attractions for me of having solar is that it's something that's under my control. So I would be interested in looking at whatever contractual language the government would eventually come up with. They're going to put something in on your system for free. So I used to read in high school a book that said there's no such thing as a free lunch. I tend to think that's the case.
And yes, I subscribe to that. And I suppose maybe that's a question for Mike Barrett more than for you, but you have a more direct line to him than I do. So please bring it up whenever you can next time.
Okay,
Thank you.
I'll do.
Bob Melanson.
Thank you, Mark, for the very interesting talk. We've talked about, I would consider the sort of alternative sources other than solar, which are nuclear and wind and the holy grail of fusion. But what I wonder about, is there any hope for a breakthrough on storage? Because from my personal perspective, that's what worries me. If I were to do this and chop down all my trees, if you could give me a couple of weeks of storage, that would change my view of it. because right now you have to keep your gas, you have to, but I assume there's a fair amount of research going on, but is there any significant improvement on the horizon?
Well, the cost of energy storage has gone down 95% in the last 10 years.
But I'm
Yeah.
thinking duration more than cost.
Well, that's how you get duration, so the duration is directly proportional to the amount of dollars you spend. That's the issue with lithium ion batteries is you don't get it, the cost is directly proportional to how much money you're going to spend on, you're buying kilowatt hour storage. Unlike sort of hydro or pumped hydro or something along that lines where your power duration is not as strongly linked to capital. So I think you're correct. The way I think about this is if I'm looking at a battery and using the battery only as backup, I can't imagine for a while that being economic. That's why I was presenting the picture of a Ford 150, which you can use as a truck and a vehicle, but also can function as a battery for you. The other interesting thing, as I mentioned before, is I think we're going to need to change state law to allow these vehicles to plug into the grid and to act on a resilience perspective for the grid. I've done a little bit of math on this, and it turns out if we transition in 2035, the Massachusetts says we're going to stop selling gas cars in 2035. And so if we figure that it's going to be another 15 years after that date before we've, brought all the gas cars off and we have 100% electric vehicles on the grid, it turns out if you do the math on how many kilowatt hours are going to be in the batteries, we will have enough in our cars to power the grid for 2 full days, sort of on average. So I think you're going to have to find a way to do a couple things with your battery storage. And I mentioned one of the things that we're doing at Hastings School with our batteries is we're lowering peak demand. And so we're getting some savings on peak demand. One of the other things we're doing with the Hastings School battery is we're participating in a program called Connected Solutions, which allows Eversource to send a signal to the battery at Hastings School and tell it to discharge when they are in need of, on a hot, peak demand day. And so we make money when we do that for Eversource. So you can start to use the battery as a resource for the grid and get paid for that. Then you start to be able to think it's economic. Otherwise, it's way, way, way cheaper to buy a natural gas generator than to buy a bunch of batteries for your house.
With my tongue firmly in my cheek, at the end of 2 days, you can have an awful lot of brick electric cars.
So I don't know.
Nope. Go ahead.
So the way I have 2 electric cars. So we get about 300 miles of range. I tend to not to need a charge. I drive around town, right? So I maybe do 10 miles a day. I can go for weeks without charging the car.
Yeah, no, I hear you.
I'm not driving to, 100-mile round trip commute. So I'm not in that situation.
As I said, my tongue was firmly in my cheek. John Brown has his hand up as the last hand.
Hi, I'm sorry, this is maybe a little bit of a downer. I wasn't going to say it, but since Tony was talking about what the government needs to do to protect the consumer, there's something consideration that I didn't even think about, but my daughter was telling me for months that she was getting solar panels, but they didn't know when they would be coming. They didn't know when they'd be coming. And I asked her a couple of weeks ago, well, what's the status with your solar panels? And she said, anyway, their solar panels were coming from a company called something like Wolf Solar or something, because they get a better deal than Sunbug Solar. And they had to put half the money down, which was $9,000, and the company just sort of like disappeared. So, and I don't know whether the state is going to be able to help her out on that, but that's just one of those things you have to worry about with all this
Yeah.
cutting edge stuff.
So I should have said it earlier in the conversation in answer to one of the questions. Somebody was saying, you know, I got a quote and then it got worse and then it got worse and then it got worse. No matter what you're doing, whether it's heat pumps or solar or getting your driveway paved, you should get 3 or 4 quotes, and probably from somebody that's got a good track record of doing business in Lexington. I'm a big fan of local. Sunbug, you mentioned, is probably the number 3 installer of solar in Lexington. A number of friends of mine have installed with their company. Revise Energy is they're probably number 5 in the town of Lexington in terms of the number. There are lots of people, friends of mine, who've installed with Revise are very happy with their service. But yes, you really don't want to go with somebody that hasn't got a long track record of happy customers in Lexington.
Ted, we got about 10 seconds, so if you can do it in that, please do.
A few months ago, the Boston section IEEE did a series of videos on these kind of topics. And to do one of them, we talked about people who had Teslas and stuff and how they interfaced. And I said, well, the other side of the interface is what happens when you plug the Tesla into the grid. So I took the simple numbers of gasoline consumption that we get from the Commonwealth, because it's a tax thing, and converted it on the DOE 37 number for electric equivalent of gasoline. And when you do that, you end up with between 2 and 2.5 times, without changing the driving habits and such, 2 and 2.5 times the current electric power handling of the grid over the course of a year. And the question is the grid able to deal with that? And my suggestion is that's probably a big issue, because a lot of people are still running circuits that are in their houses are 100 amp circuits, and the wires outside on the street are designed for those kind of circuits. So I think that's an issue has to be looked at too.
Thanks, Ted.
That's it.
People are looking at that, and you can find the ISO New England CELT report talks about this in great detail. The interesting thing that you find is that Massachusetts in 2008 passed the Green Communities Act, and the Green Communities Act did 2 things. It created Mass Save, which is, you know, the state's big investment in energy efficiency, and it created the ability for solar energy systems to net meter, to get some payment when they export solar. And as a result of both of those things, what you'll see is that ISO New England presents that for the 10 years following that Green Communities Act, the amount of peak demand on the system has declined steadily. And they project that that will continue to be the case. And they specifically point out in their reports that this is primarily due to energy efficiency investments and investments in solar energy. So what we're seeing when you sort of look at the long-term trend for ISO New England system grid, it's to reduce the amount of peak demand. Now, our utilities make money by investing in equipment in order to meet peak demand. So they like to see peak demand going up. You're exactly right, Ted, that as we add electric cars to the mix, we are going to drive that electricity usage up. I think the utilities, it will be at such a rate, this happens over 20 years, that the utilities will be more than able to.
But Mark, the relevant point is the wiring, just the wiring, not, and nobody pays for that except in your electric bill, hidden in the usage charge. It's a rare thing that they put in new wiring. They did it in my neighborhood because we're having Beirut kind of blackouts for a while because people had gone from small houses to bigger houses on the same footprint.
Right. So the other thing that you see going on that's driving a bunch of increase is people are out putting in more and more air conditioners. And in Lexington, what you're starting to see is, I shouldn't say starting, Paul knows, for the last 3 decades or so, we've been ripping down our 1,200 square foot capes and building 4,700 square foot homes in place of them. So that drives up demand as well.
Mark, thank you so much.
Very enjoyable. Thank you for inviting me.